everybody!
Draikou says, "Yay." Draikou says, "I'm looking forward to learning today."
presented by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started.
Hello everybody! I hope everyone's having a beautiful day. I want to welcome you on down. It's our first live lecture in quite a while. So let me know how the audio level is. So I will mention this probably a couple times during this live stream. Is that I can hear the chat in my ear, and periodically during the live lecture what will happen is the chat will appear on the screen, and this will be the best time for me to address questions. So if you drop a question in the chat, what'll happen, or just have a fun comment, I'll usually address it when we get to those intermission periods, or I'll try to give something as I'm doing it. So, how's everybody doing today? I hope everyone's having a beautiful day. So, it's been a while. So let me know how the volume is, if you hear me perfectly fine. The main reason why I'm asking, because again, like I said, it's been a while, and I want to make sure that the technical stuff is set up properly. But no. I just wanted to mention a couple updates before we get into things here today. So the first thing I want to point out. Okay, there we go. Now it's going good. So do keep in mind. So actually, let me just show you while I've got it here. So there's the chat there. So do note that whenever this appears on the screen, the TTS will be heard, hopefully. so do keep in mind that it's not because it's not on the screen I can't see it. I can hear it, and also I do have a monitor here to see what is happening. So just keep in mind that just because the chat isn't on the screen doesn't mean I can't see your comments. So a couple updates. So first, I've been working on a lot of things kind of just behind the scenes a bit, working more on our educational materials. In addition, I've also been working on some documentaries. So for example, about the other, would it be about, well, either way, it was around September, October, I had released a documentary with Francis Widowson. You didn't hear TDS this time? Okay, let me just quickly check that. Because it's always these little things that pop up. I'm pretty sure I know what happened. Okay. Let's see here. It should be fine. Let's see here. Just want to make sure I got it right.
Draikou says.
Okay,
There's
yeah,
also
it's
about
it.
a 10-second delay between when you speak IRL and when Twitch feeds it.
Yes, that's another thing I have to. This is why I have to mention these things. It's been a little while, so do note that there is a delay. So keep in mind, I may not respond immediately.
Actually, I think it's just because it's a lot more quiet.
It's a lot more quiet. Oh, okay. I'll bump it up a bit. So let me bring it up a bit. Because keep in mind that here, I'll bring it up a bit. Okay, let's try that. Here, I put the volume a little bit higher. Well, it's not just a little bit. I bumped it up quite a bit. If it's a bit quiet, now it's going to be...
Draikou says. So I can hear the TDS.
Yeah, okay. Yeah. So that should be a bit louder if you're trying to hear me versus the TTS. Just wanted to make sure, because you got to keep in mind that the TTS is more for us to have exchanges back and forth, but keep in mind anybody could drop anything in there. So do note that I don't want it to overpower what I'm saying here. It's more for helping.
Says, that is better. It's about on par with your voice level.
Okay. So what we'll do is I'll bump it slightly down, so that way I have a little bit of a louder voice over the TTS in the event that we have a few things going on in the chat. There we go. That should be a bit better. So just as a remark, so again, I got to say this again. So whenever the chat, the magic thing that appears right about here, when this appears, that's kind of our intermissions between different parts of the lecture. And this will be the best time for me to kind of deal with things.
Test to check sound level.
Sorry, I'm just enjoying this. But no. So what we're going to do is I'm just going to get another light on because it looks like I missed a light. There we go. That's a bit better. That's a bit better. I knew there was something I was bound to miss when we were getting this thing set up for today. But no. So let me give you a couple more updates. So first, there's a documentary. It's called The University of Regina Rumble. And in addition to this, so you can find that on YouTube. It's freely available. It's on Frances Widowson's YouTube channel. In addition, I've been working with making some of her media over there. So you can check out some of her videos. They're a little bit, I would call a little bit more spicier than the kind of stuff I put on the channel here, but they're rather important culturally speaking for Canada. So if you're just curious about some controversial issues that are particular of academic interest, that channel might be worth checking out as well. Also, I've been documenting a lot of events around the local governance around where we're located here in Manitoba. So I've been trying to do this as a matter of trying to document information for people with concerns around freedom of expression with respect to their local government. So I've been trying to document some of the interactions and talks I've been giving, or these delegations I've been giving, so that you can see those and you can make and judge for yourself what is happening. So with that being said, is everybody ready to have some fun today? I know I am. So let me know. Are you ready to go? Oh man.
Draikou says, ready.
Okay, let's get into things. Hello everybody, I hope everyone's having a beautiful day. So today we're going to be talking about Turing machines. Now, so this is going to be an introduction to Turing machines. So this is not going to be a giant kind of throw together thing about Turing machines. Instead, it's going to be introducing you to the concepts and the formal aspects of Turing machines. And we'll see where we go from there. My hope is by the next kind of section of lectures we're going to be going through, my hope is that you'll have the understanding of what a Turing machine is. We'll talk about like how you define one, how they work, and even how to design your own Turing machines. Now, you might ask, Dan, what the heck is a Turing machine? We're going to get into that in a moment, but the thing I want to make sure you know, historically speaking, is that Turing machines can be seen as, at least for the theoretical computer scientists, they're seen kind of like as the standard model for which we define many concepts and algorithms. So it has an important and rather significant way of appearing in the literature. So if you read like a lot of formal texts on theory computation, where they define a lot of core computational complexity theory concepts, they'll usually be defined with respect to Turing machines. That's not a coincidence. It's because, now this is the part that we're not going to get to today, but we will get to eventually, is we'll talk about what is a computer? Like, what is an algorithm? And I'll try to tease some of this as we kind of venture into this topic, because it can be quite deep of a topic. So let's get into things. So just the big thing I want to remind you of, so let's kind of take a little journey back. So keep in mind that we've talked a lot about theory computation here previously. So I just want to remind you kind of where we were. So kind of our journey. So here's a little bit of... So here's our journey. So just as a reminder, kind of where we are and where we're going. So we've talked about a lot of different kinds of models of computation. So this is a formal model for a computer. So rather than building a computer out of physical components, we can think about them using the dreaded M word, the mayonnaise, exactly. So one of these simplest ones we ran into are what we call finite automata. So the whole idea with the finite automata was that we modeled machines that use a small finite amount of memory. So these use a small finite amount of memory. So that's kind of like, we started off with this. In fact, technically speaking, you could think of this as like, when I say small and finite, you think of like, okay, I'm using some fixed amount of memory. Now, recall that when we looked at these, we were studying things called regular languages, when we were looking at the DFAs, NFAs, and so on. Now, what we're going to do is next after this, we sort of explored some further models, try to beef up the finite automaton. To get things such as the pushdown automata, or pushdown automaton for singular, the pushdown So what did we do in this case? Well, what we did was, instead of just having this, is so what we need to do is so what we saw with the pushdown automata was that we had the ability to have unlimited memory. And the whole idea was we used the stack to keep track of that memory. And we talked a lot about these when we were talking about these pushdown automatons. Now, in about 1936, a fellow, he's a rather influential figure in the history of computation. Around 1936, a fellow named Alan Turing came along. What happens is that Turing was very curious about this idea of there being, if you wanted to imagine, especially during Turing's time, there are a lot of very fascinating and open questions around mathematical logic, where the real question was, how can you formulate the idea of any possible computation, any possible computation. And what Turing came up with, now Turing obviously didn't call it this in his time, he called it something else. But what we're going to talk about is we're going to find something equivalent to this called a Turing machine. Now, this idea of any possible computation, I want you to kind of keep this in the back of your mind. Just like take this thought, just like put it behind your ear. Think of general purpose computers, because I'm not going to prove it here today, but the idea will be that if I can capture formally any possible computation, then most certainly any general purpose computer, including what you're probably watching this on, is capable of being simulated by such a machine. That meaning that this has the ability to match this capability and possibly even have even more bells and whistles attached to it. So really, if you're wondering why Turing was interested in this, as opposed to, say, you might think of like a neat computer or something, Turing was very interested in this question of the following. And I'll keep this high level because we can get very deep with this topic, okay? So, is what problems can be solved with computers? And I mean, like, I don't just say like your laptop or your desktop or your smartphone. I mean this in the broadest sense. I mean like any computing machine. So this is a fairly deep question. Because if you could answer questions about this, then this has deep ramifications for what? So if somebody throws a problem at you and you start asking yourself, okay, how do I solve that problem? Well, if there's a way to formalize this and maybe use these ideas that we're going to see here, maybe there's some way that I could say, maybe it's not actually able to be solved. Like maybe there is no algorithm, aka what we're going to see is a Turing machine, for which I can decide that problem. Meaning that there is no way to actually solve it. There is no algorithm. Hopefully I get to a little bit of motivation of why we might explore these. So keep in mind the Turing machine itself, I must stress, it's not going to be like your high-spec computer or something. In fact, technically speaking, comparing it to a general purpose computer that you might be used to, it'd be seen as rather slow. But don't let the fact that is the case throw you off. This is about capability, not efficiency. But the other neat thing about this is since this is a formal model, you can execute this machine out on paper just like most computers. Just we're talking about something fairly simple. And the idea is you want a very simple model so that you don't have to think about these big, complicated systems of transistors and all this other stuff. You can instead think about this very simple model. And that's the idea, is if you make a very simple model for describing computation, then you can make broader implications if you can show that your more complicated computer can be simulated by this much simpler one. But we'll talk about that in the future. I just wanted to motivate this to give you some historical background. So do note there's a lot of interesting history around these questions that are around Turing's time period. A lot of this is called computability theory. So this is like at the bedrock of computer science. In fact, one would argue that what Turing did, as often is considered one of the founders, if not the founder of theoretical computer science, and hence computer science itself, what he did was he showed how we can come up with a machine and showed how to smash it. And by smashing it, I mean answering questions like this. So let's get into talking about this. And I don't want to get too formal right away. So let's go over here. Let's go over here. Give me one moment here. So let's head over here. I'm going to try to give you a picture because we need some understanding of what we're looking at before we get kind of into the weeds of this thing, okay? So I'm going to draw you a picture. So this machine is going to have what we're going to call a finite control. So this finite control, keeps track of the present state of the machine, and it has several parts to it. Namely, it's going to have a read-write head. It's going to have this head. So we'll often call this the tape head. So this is called the tape head. Sort of fun, we're kind of imagining this machine, right? Like, I'm not like building the machine, I'm imagining this machine, okay? So this will keep track of the state, and the instructions of what we're going to do are here. But here's the thing that this Turing machine does, is it has a tape that it can read. And what happens is this tape head, when the machine starts up, it starts off on these different tape cells. So this is our tape here. And this is what we call a tape cell. When the machine begins, it will start by having the tape head positioned on the leftmost tape cell of the input. So when this machine starts up, what's going to happen is it's going to have the input loaded up. It's going to be on this tape. Each of the symbols for this tape are going to appear from the first position of the tape head, where it's located, and it's going to go to the right here. So say the second symbol will be x2 here, and so on, and there'll maybe be some xi, and then there'll be some more tape cells, and then it'll be xn. Maybe that's the last symbol in the input. And you might ask, okay, well, what's going on outside of this? Because you have this big tape, right? Like, is this like you got to think about this, okay? So this is supposed to be like a tape. And now, for those that might be thinking about this, maybe just because of the way I'm talking about this. So when I'm talking about this as a tape, I want you to think of this as a record. Now, some of you might know what a cassette tape is, for example. There's a lot of different technology around tapes where it's recorded on the tape, and each one of these cells, if some of you might even be familiar with something like film has film cells. This is very much the same idea. So when the machine starts up, my input goes, so my input will be loaded here. And to the left and to the right of it are going to be what I'm going to call blank symbols or blanks. So these I'm going to have these, what I'm going to call, I'm just going to put a big B. So all of the other tape cells are going to have blank symbols. Now you might ask, Dan, is this like chopped up? Is this like a piece? Is it like a finite thing? Well, just keep in mind that this thing, now this is where it gets, you got to use your imagination a little bit, is while the machine itself will use some finite amount of memory when it begins, if I want to use more tape cells, the Turing machine is more than capable of doing so. So whenever I need more tape cells, I can simply read or write with this tape head. So remember, this can read or write. I can read or write with this tape head. I can use more cells if I need to. So keep in mind that you might ask, okay, well, how many tape cells can I use? And this is actually an interesting question in its own right that we're not going to talk about here, but you can talk about questions of how much memory is used by the Turing machine in terms of these tape cells. But the Turing machine itself is allowed to have as many tape cells as you need to execute the process on the input. So remember, this right here is the input. It may change the behavior of it based on what is encoded as the finite control of the machine. But here's the catch. You always have as much as you need for memory. So it means that if you go that way, say if this tape head, because the tape head, what it does, as I'm going to explain to you in a moment, it's going to go left or right a cell, and it's able to read or write to a cell. So for example, if I were to if say the 0 was here, which I'll give you an example in a little bit. If it's a 0 here and I want to write a 1 here, I can read or write a 1 here. I could then make it so the tape head moves to the right. And then I can have it so I can put a 0 or 1 there too. The whole idea is that this tape head can move left or right. And I can potentially move it onto one of these spots with the B's, these blanks. If that's the case, I can even write here. But here's the thing. The tape goes all the way this way. The tape goes all the way this way. And I mean all the way. So it means that I always have as much as I need. So when I'm saying it goes all the way this way, it continues to go on, what I'm saying is I can always have as much as I want. So when I'm saying this much, I'm actually saying it's not even this much. So keep in mind, it goes on forever. So it's an infinite tape. So it could go on forever. So just keep that in mind. We never are bounded by the amount of memory we need. So now let's just kind of summarize what I just said here, because I'm getting really excited. I hope you're getting excited too. This is pretty interesting because we're imagining this thing. And some of the models that we've looked at, including the ones I just mentioned a little earlier, some of these are actually quite complicated. Like the pushdown automata, the way we formalize it's a little bit tricky if you're not used to seeing it like that. But this thing has 3 parts. So it has the finite control. So this will be in any finite number of states. So I'm just going to keep it broad. So a tape, so that's a part of the machine. The tape that is divided into squares. So it's divided into squares we call cells, or tape cells. Called cells. Each hold some finite number of symbols. So we will think about it for us. We'll think of it holding one symbol. So like a 0 or 1 or a letter. Now, just keep in mind, at the beginning, don't mind me, my writing is sort of melted in the microwave like a piece of cheese. So at the beginning, especially that T is not looking very happy, and that G is looking a little excited there. At the beginning, the input is placed onto the tape. Which, remember, this is a finite string. Just keep that in mind. It has to be a finite number of symbols because it's the input. Placed onto the tape. So that's the second part. And I already told you how this goes infinitely to the left or to the right, where all the other symbols are blank symbols. So remember, we designate them as blanks. So we can give them another, like if you didn't like these B's, you can put something else there. If you want to put a little happy cat there in every one of the cells, you can do that. You can put a happy little cat in every one of those cells if you like. But these are the blanks, these B's here. So let's get into this. Now the third one, of course, I said was the tape head. So keep in mind that the tape head. So let's talk about this tape head. So we have the tape head. So the tape head that is at one of the cells, that is cells which allows the Turing machine to scan a cell. Right? That's very important. It's got to be able to scan it. So I'm just going to put in parentheses that it begins at the leftmost cell holding the input. So just keep that in mind. That's what we're going to follow for us. So just keep that in mind, because there's a lot of different conventions people have for Turing machines. And here's the fun part, is even if they're described differently, there's going to be some equivalent Turing machine. So if you don't like the way I present this Turing machine to you, there might be an equivalent definition of this Turing machine for which it follows somewhat different rules. So just as a reminder, just remember, we have the finite control, we have the tape head, and we have the tape. So as long as you remember there's these three things, and this tape head's going to be able to move, which now I'm going to talk about. So let's head over let's head over this way. Let's go over this way. So we have those three parts. So I told you how this tape head's going to move left or right. So let's talk a little bit about how that works. Just scrubbing away here. I think the mixture is a little too strong. That's just about got it all. Okay. So, now we got to talk about a move. Now, this conception of a move is very much like with the push-down automaton. And let's talk about it. So remember I said how this tape head's going to be able to move left or right. So a move. So this is like an action of the Turing machine. We're going to call it a move. A move of a Turing machine, which I'm going to start abbreviate Turing machine as TM. Depends on the state. Depends on the state. So this is from the finite control. Depends on the state of the finite control. The finite control. Finite control. And the tape symbol scanned. The tape symbol scanned. Where it will follow the following sequence of operations, okay? So it's going to always do the following. So keep in mind this order for which the machine will execute the move. Where it will. So it's going to perform them in this very specific way. So I want you to imagine I got my tape over there, like we kind of visualized for a while over there. So the very first thing it's going to do is it's going to change state. So if it has a state it needs to move and transition into, it most certainly will. So it will change state first. This may be to another state, or remain in the current one. Or remain in the current one. Now, once it does this, it's going to then write a tape symbol. It's going to write a tape symbol. Now, I haven't really told you what a tape symbol exactly is. I sort of gave you this idea that there's this thing that happens where it scans the tape cell or the cell. It's going to potentially change state. Then it's going to write a tape symbol. So this machine's going to have these things we're going to call tape symbols, which I'm going to define in a bit. For which that's the symbol you get to put down. So you know when I was talking about, oh, well, what if I want to write a 1 to the tape in a particular cell? Those would be tape symbols. Write a tape symbol to the scanned cell, which it must be stressed, it's okay if it's the same symbol that was already there. So which may be the same symbol as was there before. So just keep that in mind. So we're going to have it where change a state, write the tape symbol, then it does something. What was the thing I kind of didn't really I suggested this tape head has this functionality, but what was the thing that I said, this thing that the tape head is capable of doing? There was something it was able to do. What was it? So I'm missing, so this is the last step it's going to perform when it does a move. What do you think it is? What do you think it is? So there was something that this tape was able to do. Like, sorry, the tape head was capable of doing. So most certainly it doesn't, like, stay in one spot, right? What does it do? What does it do? Well, yeah, it's going to move, right? Well, like, when I say move, like, it's got to move in some direction, right? It's got to go left or right. That's the... So then it will move the head left or right. So it moves the head left or right. So just keep in mind that we will assume the following. It has to move left or right. It's not allowed to stay put. So it has to move left or right. So just keep that in mind. So we will assume the tape head must move left or right. It has to be left or right. It cannot stay on or at the same cell. But it must be stressed, just because we're assuming that it must move left or right on a move, that does not limit the capabilities of this machine that we're talking about here. In the future, I will show you that this limitation doesn't actually change its capabilities. Like, if I added that feature, this machine will still just be as capable. It just won't have this just doesn't have the feature. So I just wanted to plant that thought for now, just so you can think about it. So just to summarize, move, 3 parts. It changes state, it writes a tape symbol to the scan cell, and then it moves the head. So just remember, change state. Then what was the other part? Oh yeah, we write the tape symbol, and then we move in a direction, right? We move one cell to the left or one cell to the right. So now I can tell you about how we're going to define our machine. Now, for those that have seen what we've discussed when it comes to our definitions, this will look a little daunting, but I want you to remember this picture here, okay? So just don't let the fact that this is going to look a little intimidating. I must stress, for those that have seen the push-down automaton, or you'll see that this is actually a little bit simpler in its definition. So it's actually not that scary. So that actually makes it kind of nice. So just keep this in your mind as I'm going to define the Turing machine now for you. Ooh, this solution's definitely going to need to use a little bit more water in this. The whiteboard marker is a little sticky. Just going to take away the 3 parts. So we're going to need space for this. I'll keep the picture there because the picture's fun. Just gotta get it out. There we go. Okay, so here we go. So now we're going to define the Turing machine. Now keep in mind, this is how we're going to define the Turing machine. Do note that there's several equivalent definitions of a Turing machine. So just keep that in mind. So I'm going to abbreviate as TM. So I don't mean trademark. I mean Turing machine. So here we go. So it's going to be a 7-tuple. A 7-tuple M, which is going to be equal to, so here's the 7 parts, and some of these are going to be very familiar to you if you recall how we defined a deterministic finite automaton. But it'll have some elements that we've seen with push-down automata, but it's going, remember, this machine, just keep this in your mind, is that this is a deterministic machine. It's not like a PDA, which is non-deterministic. So, we've got Q, sigma, capital gamma, delta, Q0, the blank symbol, and F. Where? We're going to define them as follows. Now, a lot of these I've already actually gone through, so instead of me going and listing them out very carefully for you, I'm going to get through all the ones that you're familiar with, or might have a good idea what they are. So this is the set of states. So this is your finite set of states. So these are the states. So those are the states of the machine. These are your input symbols. So these are the symbols that are used when you give somebody the input. So just keep in mind that the input symbols, those are for giving you the description of the input. So these are your input symbols. Now, these guys, these are new. So let's kind of go past this one. This right here, we usually use delta for the transition function. We'll talk more about that in a moment. This right here, well, that's the start state. We always tend to have a start state. So we have a start state. We talked about this special symbol we call the blank, or the blank symbol. So do note that this is the blank symbol, which I must stress must be a tape symbol. That's the blank symbol. And you might guess what F is. Well, F, these are your set of final states. So these are the final states, the final or accepting states. So a lot of these components, so this is just a set of them. It's some subset of all of the states. So we have set of states, input symbols. We're going to have what we're going to call the tape symbols, the transition function, the start state, the blank symbol, and the set of final or accepting states. So this is the formal description of a Turing machine, but I need to now give you the parts I have not drawn arrows for, okay? So, where gamma are the tape symbols. So do note, this is worth noting. So note that the input symbols are a subset of the tape symbols. So that means that whenever you use input symbols, they must belong to the tape symbols. Why? Is because the tape, remember your picture here, we got our picture over here. We have these tape cells, right? When I put the input down on the tape, what's in these cells? Well, these are input symbols, but they're on the tape, so most certainly they must be tape symbols too. So that's all I'm saying here. But it's saying that I can use more symbols if I want to write things down on the tape. That's all I'm saying beyond that. So these are tape symbols. Then next we have the transition function. Now, it's worth noting, just as a reminder, that the set of final states, again, subset of the set of states. But now let me define delta for you. Delta's got a few pieces to it. So delta, so I'm just going to write over here. So I'm just going to take an arrow and I'm just going to whoop, whoop, there. So we're going to talk about the transition function. Is a transition function. So this tells me how to perform these moves. So that's the big thing you just want to know about it. It tells me how to do these moves. Is a transition function. Now, don't let the notation scare you. It's really not that complicated. So remember, it's just stuff to make a good sandwich. It's the mayonnaise and mustard to a good sandwich. So just don't let it spook you or anything. And has the form. So it'll take in two inputs. So delta, it takes in two. So the first parameter, this is a state. So it's some state. So it takes a state. So that's a state. And you might guess what this other thing is. Well, think about our picture here. What did the finite control do with the tape head? Well, it goes, it scans the tape cell. What are these though? What are those? I'll give you a hint. I just told you about this. They have to be, what are they? They're tape symbols. They're tape symbols. So let's see what we got here. So we have, so this capital X, this is some tape symbol. So it takes a state and a tape symbol and it does something for us. So if defined, because we're going to allow the transition function for particular states and tape symbols to be undefined, which I'll talk about in a moment. If defined, the input, actually, now let's talk about the output. The output of delta QX has to, so remember, just think of the machine. The machine, it's in a state. So it might be the initial state, the start state. It could be a state that maybe it's scanning some part, maybe it's going left and right on the tape or something. It's some state, it reads a tape symbol, it's got to do something. So we have to describe a move. So remember, what was about a move? How do we describe moves? There were three things, right? Can anybody remember those three things? So we went through those three steps on a move. What were the three steps? So what were they? So if I want to describe what a move is, so I read the state, I have a state, I'm in a state, sorry, I'm getting very excited here. If I'm in a state, I read a tape cell. I want to do something. What were the three steps? There are three steps. The output of delta QX is a triple. So it's a three tuple. A triple. P, Y, D. Now you might ask, what are these? Well, they're the three things I just told you about earlier, right? What are the three steps? Change to a different state or stay in the same state. What to write to the tape cell, which tape symbol to write to the tape cell, and the direction, left or right. That's what this transition function will give you if you give it a state and a tape symbol. If it's defined, we're going to allow it to be undefined. That's a very important feature of how I'm defining a Turing machine for you, is it's allowed to have it where it's not, doesn't define the transition. I'll talk about that. But it's going to have three things, and these are the three steps, right? Change state, write tape symbol, move direction. So move left one cell, move right one cell. That's really it. So just as a reminder, show this right here. So this is the next state. So it could stay in the same state. So this is the tape symbol. Sorry, I'm getting really ahead of myself. Tape symbol to write. So we're going to write in the current position that tape symbol. And then we're going to have a direction. So we have the direction. So this is the direction where D is either L or R. Where L means left, R means right. So this indicates if you're going one tape cell to the right or one tape cell to the left for R and L respectively. Pretty neat, right? So this what I've just done here for you. So this defines what a Turing machine is. So now that's a lot to take in all at once. So I want to just give you some important remarks about how this machine works with all these bits and pieces now. So just remember, it has a set of states. We're going to see a lot of examples in a little bit showing what this might look like. But don't worry. If it looks like a lot, don't worry. We're just sort of coming up with a formal description for our machine. Gotta put my arm into this. Oh. I really have to put my arm into this. So I don't know what's in these markers these days, or it's the solution used to clean this. It could be a bit of both. I could have put my little penguin friend back up there. So what we'll do is we're going to keep our 7 tuple up here because that's a lot of stuff all at once to take in. So I'm just going to keep this guy up here so that we have that as a point of reference, just for a little bit. So get my little penguin friend. All right, there we go. There we go. He's back. So now that we've defined what the Turing machine is, I have to give you important assumptions and remarks about how it works, okay? So these are very important to keep in mind for our definition of a Turing machine. But there's many equivalent ways of describing these same things. So just keep that in mind as well. So if you might say, Dan, well, when I heard about a Turing machine, it didn't do this. That's okay. There might be some equivalent way to describe the same thing. Just it's not necessarily in this functional way. Again, like I said, there's many equivalent definitions for Turing machines. You'll find that this one's rather intuitive if you want to think of the machine having to stop at some point when it finishes processing. So So here we go. So these are important remarks about the transition function delta. So this is actually a component of how I'm defining delta for you, where a Turing machine is in a state Q scanning. Ooh, that end's looking a little sad. There we go. Scanning tape symbol X. So let's talk about this. So I have to define something we're going to call halting, or describe when a machine halts. So now I need to talk about that. Because certainly we don't want this machine to run forever. It has to stop at some point if I want to get an answer. So I'm going to consider this idea. So keep in mind, the Turing machine, if I didn't have this concept, Turing machine, technically speaking, could run forever. And there is nothing inherently wrong with running forever. It's just that when I want to solve a problem, usually I want the answer, right? But getting the answer means I need to stop at some point. So let's see. A Turing machine halts whenever delta Qx is invoked, but is undefined. So let me explain what I mean by this. So we had our picture over there of the Turing machine. Remember we talked about what a move is. It had 3 steps to it, right? Change state, right tape symbol, move left or right, correct? So that's when it's defined. If it's not defined, then there is no move. But logically speaking, what does that mean if it has no move? Well, it means, what does it mean? It means it stops. It has no way of moving anymore. That's all I'm saying. So that's what it means to halt. So a Turing machine halts whenever it has no defined move. So this simply means the following. There is no move. So it stops. Right, that's it. So that's how the machine can stop. Some people call this crashing the Turing machine. I prefer just talk about it as halting it or stopping it. But you'll sometimes hear people talk about crashing the Turing machine. This is how this is discussed typically. So now here we go. If we're interested in this machine being able to accept or reject input, we need some way of defining that for us. Keep in mind, Turing machines, as I'm going to show you in a little bit, are able to use to do processing, where you actually do some processing on the input and you get some output that's left on the tape. So it's very functional in that way, and that's actually how fellows like Turing thought about these machines, or machines like these ones, to be a bit more accurate. So if the Turing machine is not in a final state, so it's not one of the states F, it's not one of those states, it's not in a final state, when the machine halts, so when the machine halts, it rejects the input. So it's going to reject the input. So if you had a question of like yes or no, accept or reject, what you would do is you would want to make sure when this machine, it's not in any state that belongs to this set of states, the set of final states. If the machine halts, meaning there is no move it can take, then it will reject it. Now, so you might ask, oh, wait, what about acceptance? When a Turing machine is in a final state. As the name suggests, the Turing machine halts. Now, I must stress, this is actually a really important technical assumption I am making, is that you could think of it like this, but when we actually design the Turing machine or build a Turing machine, what this is saying is that we do not define the transition function on any one of those tape symbols for a final state. That's all this is saying. So you can actually straight up define the Turing machine so that it has this behavior, but we're going to force it to have this behavior by not defining transitions on final states. So some people call them halting states even. So just keep in mind, when I say this, you're just going to make sure that Q, delta Qx, undefined, on all final states. You'll see this when we get to some examples. So this will force it to stop. So now we can talk about acceptance now. So if it gets into a final state or accepting state, same thing. The Turing machine halts. So now I can talk about what it means now to say, well, okay, with the Turing machine. So now we have kind of like the symmetric version of what this is. So if the Turing machine enters a final state, so even it just enters it, it accepts the input. So do note, the typical definition you'll run into is that if it enters the final state, then it has to accept. This part I've added here about trying to make it so it halts, this is actually just a truncation of the computation. So do note that it really doesn't change anything, it's just that we'll typically make this assumption. It doesn't do anything magical or limit what we can do with these machines at all. But I need to stress that it makes it sound like that there's, like, say, well, I talk about halting, right? Well, there's sort of, it seems like I'm suggesting to you by this that the Turing machine has to always halt. But that's actually not true. So there's a very important warning, okay? Turing machines are not guaranteed to halt. So just keep that in mind. That's a third possibility. So it could accept, it could reject, or it could never halt. Meaning, so if you think about this like computer programming or something, think like an infinite loop, for example, where the program continues to process, and it will continue to process, but it will never stop. So you have three different possibilities. So this means the third possibility is that it neither accepts or rejects. Input is possible. So that's a possibility. So it can't halt, so it can't tell you accept or reject. So that's a very important thing to keep in mind. So I want to give you an example. Let's have some fun with this, okay? So let's have a little bit of fun with this. Let's get rid of our lovely picture. Bye-bye, beautiful picture. Whoops. As I'm obliterating the board and myself and the whiteboard eraser. I told you there was going to be some fun things about this stream. Indeed wants to live. It seems like everything wants to live. The whiteboard eraser, the marker, like the markings. Nothing wants to leave the board. I'm just going to try using the other eraser. Told you something fun was going to happen. I'm going to get the other eraser. Let's try this up. Just gotta put my arm into this. Don't need any more casualties from me erasing the board. It's some serious business. Okay. There we go. So let's consider an example. Let's consider this the following example. So we're going to consider Turing machine M. We're going to consider Turing machine M, where it's going to have the following. It's going to have two states, Q0 and Q1. Q0, Q1. For its input symbols, it's going to have the letters lowercase a and lowercase b. For the tape symbols, it's going to have lowercase a, lowercase b, and the blank symbol. And the blank symbol, we're going to have delta, which I'm going to define in a moment. We're going to have Q0 be the start state. We're going to have capital B be the blank symbol. And the set of final states is just going to have one state we're going to call Q1. Okay. So this is a description of a Turing machine, except I'm missing one thing, delta. So I need to give you delta. There's several ways I can define delta for you. I could define it formally using the notation I've described to you. I can use a transition table, as I've done in the past with different types of machines. I can also use a transition diagram, which I'll show you an example of those in a little bit, where delta is defined as, so delta, so on Q0, when it reads an A, it's going to do three things, right, on a move. It's going to stay in Q0, it's going to replace the A with a B, and it's going to move right. So remember, that means right, move tape cell 1 to the right. So that's what so if I give you Q0, and I see B on the tape cell that the tape head is reading, it should be Q0. It's going to keep the B there, and it's going to move right. And let's define on Q0 on a blank. So if it sees a blank symbol, it's going to go Q1. It's going to move into Q1. Remember, that's a final state. It's going to write a blank, so it's not going to change the symbol there. And then it's going to move the tape head left. And for all possible pairings of the states with tape symbols that I have not defined of these three, assume they're undefined. They're undefined otherwise. So it means if I give you one of those inputs, stop moving, halt. That's what it means. Is that clear, everybody? Hopefully that's clear. So now let me show you what it does with some input now. Because I think having the abstract picture with the tape cells with all those X's and stuff was a little abstract. Let's start with something really simple, okay? So let's consider some input. Now, remember, the input symbols are A and B's. So any combination, including, technically speaking, no A's and B's, can be given to this machine. So I could give you like A, B. I can give you B, 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 B. I could give you 10,000 lowercase b's, 10,000 A's. I could give you the A's and B's like this. Those are all there's many different ways I can list out those input symbols. That's the way I'm describing the input to you, is I give you some string of A's and B's. But here's a particular one. As an example, let's consider W, which this is going to be the input string. Say we have BAA on M. So let's see what that looks like. So let's walk through everything that we just applied. So all those abstract ideas, we're going to make this very concrete now. So here's the tape. Here's the tape. Here's the tape. It goes forever that way, forever this way. And I mean forever, okay? So there's a blank there, a blank here. So that means I need to put don't remember when this machine is going to start, you put the input on the tape. So I need BAA. And notice that, remember, where does the tape head start? Where does it start? Does it start right here? Does it start over there? Does it start like over here? Or does it start like here? It starts on the leftmost symbol of the input, right? It always starts the first symbol of the input. So, well, what's the start state? The start state is Q0. So it means that the finite control will be in Q0, the tape head is pointing at lowercase b in BAA. So this is the initial configuration of this Turing machine for this particular input. So now we're going to see what this thing does. Let's walk through this carefully, okay? So let's see what it does. Is everybody excited? I know I'm pretty excited to see what this does. So we're going to now walk through this process. So let's see. So it starts, it's state Q0. It reads a B. So it says, okay, well, let's look for the appropriate one. If there is none of them here defined, I'm going to stop. So I see Q0 with an A. No. Well, Q0 is currently reading a B, right? So Q0 and B, it says, okay. It says you're supposed to stay in Q0. So you're supposed to stay in the same state. You're supposed to replace whatever's there with a B, which B's still there. And we're supposed to move the tape head to the right by 1. So here we go. Okay, so it says, okay, well, I change the state. Q0 is still Q0. I write the tape symbol. Okay, B is B. And it says, move right. So let's move the tape head 1 to the right then. Okay, so now we're in the next. Now we did one move, right? Sweet. We did one move. So that's a move of the Turing machine we just performed. So nothing really interesting has happened. It's in the same state. We haven't modified the contents of the tape, and all we did was we moved right once. So let's see what happens now. Okay, so Q0. So right now, state Q0, we read the cell that has an A in it. Q0A, it says, okay, stay in Q0. We're supposed to no longer have an A there. Time to write a B there. It says to write a B. and it says go write one tape cell. Okay, we just performed our second move. Let's try another move. First, can we perform another move? Let's see. Right now it's still Q0, and we have an A. Yeah, we could certainly perform a move with this machine. Q0, A. It says, okay, well, it's the same thing we had before, right? So we're supposed to take that A. No way, or A. I don't want that A. A. It replaces it with a B. Remember, what was the thing I forgot to do? Ah, yeah. Q0, it's still Q0, right? Then I changed the symbol. Now I'm going to move, right? And it says go right. Okay, well now we're at a blank symbol. So we performed the third move, and now we're on the blank symbol. Well, it says Q0 when I read a blank. It says move to, so we're going to change states to Q1. So it's going to change to Q1. Write a B there. Well, it's still a B, so you have blank is blank. And it says, okay, go left. Go left one cell. Okay, we go left one cell. Now, notice, we're in state Q1 now. Do you see anywhere in this list of possible transitions? Do you see a Q1 anywhere other than as a state I could move to? No, right? It's undefined for anyone. So there is no Q1 with a symbol, Q1 with a symbol. There are only Q0s here. So if it's undefined, then we halt the machine, right? So that means that this machine is going to halt. And now let's ask the question. Does the machine accept or reject? Does the machine accept or reject? Well, let's try to understand this. Remember, we have the states, input symbols, tape symbols, transition functions, start state, blank symbols, set of final states. So the very last one here is the set of final states, and it has Q1 in the set of final states. So by our definition of what it means to accept, does this machine accept or reject the input? Accept or reject? Which one is it? Which one is it? It's halted. It's halt. The machine halts for this particular input, but does it accept or does it reject? Well, let's see. Let's in state Q1. Q1 is one of the final states, so it has to accept. So it accepts the input, W. So it accepts as Q1 is in the set of final states. Neat, right? Now I have a question for you. Question. What exactly is this Turing machine doing? What is it doing? Does anybody have any ideas of what this Turing machine does? What's it do? Is it like, it seemed for our input, it took any of the A's and turned them into B's. Do you think that does that more generally? Maybe it does that more generally. Let's see. So it stays in Q0. So whenever it reads an A or a B, it just changes them all to B's and always moves to the right. So it appears that if you use this Turing machine, what it does is it just seems to take any one string and it just, of A's and B's, the way we have them, and it just turns them all into B's, then it accepts. Which that's not terribly interesting, but it's kind of neat because it sort of does this functional thing, right? It's going to turn them all into B's, then it accepts. So it means it's going to accept on any one of the any combinations of A's or B's, which is neat, right? It's kind of neat. We can transform the input string, which we'll see that idea later on when we talk about something called transducer, where maybe this idea of accepting isn't terribly helpful for us. Instead, we want to convert the input into some output. So you might ask, okay, so what exactly does this look like if I try to visualize in a few other ways? So So one way I told you how I could define delta, by the way, is using a transition table. So let me describe the transition table. So if you don't want to explicitly define it like this, I could give it as a table instead. So here's a transition table. So we're going to have our states. We have Q0 and we have Q1. It's going to have A and B and blank. These are our tape symbols. We're going to have a column for each tape symbol. We're going to have a row for each one of the states. Do note that often by convention, you make the final states, you put little stars beside them. But for the sake of simplicity here, I'm just going to not do that just because I don't want to add additional steps we don't need to talk about here. So do keep that in mind. That's a common convention. So, okay, so what do we have here? So it had Q0A, so at each intersection of a row and column, it says this on the state Q0, on an A, it's supposed to do something. We put the triples inside of each of the table cells. So now, each one of what we have up there, so it would have Q0, lowercase b, right? Q0 on B, Q0 on B, Q0 B R. Q0 B R. And when I read the blank, remember, if it's in state Q0, if it reads one of these tape symbols, if I look at where the two intersect, it tells me what I'm supposed to do on a move. So, if one says it's supposed to go to Q1, keep the blank, and then go left. And remember, I left all of the others undefined, so they're just... So do note, whenever I give you a final state, as I said earlier, it's going to be the case that they're not going to have any additional moves that happen once you enter the final state. So always remember that. That's a very important part of our definition for the Turing machine. So this just shows you a transition table for our Turing machine, which I've defined formally the transition function here. But here I've given you what it looks like as a table. So let me show you what it looks like as another visualization. So let's draw a picture over here of what this Turing machines might look like as a transition diagram. Ooh, it doesn't want to move. Okay, so now I'm going to define the transition diagram for this Turing machine I have over here. So I'm just going to follow conventions quite similar to those which I've given for deterministic finite automata, but also for pushdown automata. But I'm just going to show you how we're just going to describe it ever so slightly differently. So again, we only have two states, Q0 and Q1. So I'm going to have two states, Q0, Q1. Q0 is the start state, so I'm going to indicate that as the start state. And now, Q1 is one of the final states, so I'm going to double circle it to indicate it's a final state. So keep in mind that this diagram will help me if I follow my finger around where it transitions, it'll allow me to see how the execution plays out. So the flow of execution. So let's walk through what we have here. So I'm going to show you how I represent this. So on any undefined transitions, I don't draw anything. However, for the ones I've defined, I'm going to add in these directed arcs, or the arcs, sorry, to be a bit more precise, they're arcs or directed edges that are going to represent those. So the convention we're going to follow is that I have the symbol I'm reading. So if I'm in Q0, if I read an A on the tape cell, I'm going to put a slash, and it tells me what the symbol should be replaced with, as in what tape symbol to write, and it indicates the direction. So if I were to follow this carefully, what I'm saying is if you're in Q0, you see an A, it says, okay, replace the A with a B and go write one tape cell. So you'd follow that if you read an A on the current tape cell. Likewise, if I have a B, I'm going to keep the B and I go right. Notice that these two I've just described here correspond to these two right over here. Hopefully that is clear to everybody. Now, we're missing one. We're missing this one right here. So let me describe that. So this is going to take me from Q0 to Q1. So we read on a blank when you're in Q0. So if I'm in Q0 and I see a blank, I'm going to follow this. It says to replace the blank with a blank. And then move the tape head left one. One cell to the left. So this is, in fact, a transition diagram. So this is a transition diagram. And this is for M. So this is for our particular Turing machine. What I have over here, down over here, that's a transition table. Do note, again, I'm not using the conventions here that are very common for transition tables, such as using a little arrow and a star for start and final state. So just keep that in mind. So that's just a concrete example. I'm going to show you one more, just because it's a good idea to see one more before we get into kind of our next thing. So let's do another nice, simple one. So this one's not terribly interesting if you're thinking of this like, oh, what kind of languages can I describe? Like, so let's pick a regular language that has some kind of meaning. So let's do another example here. So let's make a Turing machine that accepts the following regular expression. So it'll be a 0 star. So we're going to make a Turing machine that accepts on any string that is of this regular expression. Now, for those that don't know how to read a regular expression, all this is saying is the string has to have the following form. It has to have a 0, and then it has 0 or more zeros. So for example, a string like this, that most certainly is described by this regular expression. This is described by that regular expression. This is described by that regular expression. So it has to have a 0 at the front, but it can have 0 or more zeros after it. However, something like this, that is not, because notice it has to be a whole bunch of zeros. It has to be 0, and they can have 0 zeros, 1 0, 2 zeros, 3 zeros, and so on. So we're going to make a Turing machine that's going to only accept strings that are of that form. So these are okay, that's okay, that's okay. This is not okay. No, not okay, not okay, not okay. So let's do this. So this one, so let's consider a Turing machine. We'll call it M2. As described by the following transition table. Where the set of final states is going to only consist of a state called Q2. Now, and start state Q0. So I'm going to have a final state. It's going to be Q2. It's going to have a start state, Q0. Now, for the sake of brevity, I'm just going to ask you as a little exercise for yourself to go and describe the 7-tuple for this Turing machine I'm going to give you. So I want you to look at the transition table, and this is something I'll get you to think about on your own. Given this information, I want you to think about how you would give the 7-tuple or even draw its transition diagram. So here we go. So notice that here I'm thinking of binary strings. So I'm just curious about binary strings here. So suppose that we have binary strings. So it's going to have states. We're going to have 3 states. We're going to have Q0, Q1, and a Q2. We have 0, 1, and a blank. Now, we know right away the 1 column should be very interesting because the minute you see a 1, you're supposed to halt, right? Because that's a bunch of junk. You don't want the 1s. You only want it when it has a form with 0 in it, right? So the minute you see a 1, you better halt, and it better not be in a final state when it happens. So let me just fix up that B. That B is looking like it's going for a little trip. There we go. So it starts off in Q0. Its final state is going to be Q2. So when we get to Q2, that's what we want. Now we're going to try to adapt some of the ideas that we've had up to this point. So notice that I can basically have it so it can scan from left to right. Now this at first will look very natural to do if you're familiar with deterministic finite automata, because that's it. You can look at the DFA like a special case of a Turing machine for which the head always moves 1 to the right. And then it's ultimately determined if it accepts or rejects if you're in the appropriate state. So you can think of it as a one-way read-only Turing machine where you just make a few little things you got to squint at. So I want us to think a little bit more about how we might do this. So first, we know we have to have at least 1 0. That we know as a matter of fact, right? Because there has to be at least 1 0 at the front, right? So we know if we see a 0, we don't want to halt right away because we might need to read more zeros. Because just in case there might, because remember, one thing we also don't want, we don't want things that look like this. Like where it's 0, 0, 0 and then has a 1. We don't want that. So we better not halt and try to accept right away. We need to make sure we don't run into any 1s. Sorry, I'm getting really excited here. So what I'm suggesting is that, and you'll find that when we get more and more complicated Turing machines, that maybe even we want to give these states names that are kind of like jobs that they have. So we're going to dictate if you see at least 1 0, we're going to go into this new state, okay? So maybe if you want to colloquially think of this as the okay-ish state, that's kind of what you can think of this like. So we have Q1, 0, and we're going to go to the right. We just want to keep reading zeros if we can. Most certainly, if we see a blank, we don't want that, right? Because remember, the empty string has no zeros in it, so we do not want that. So we will certainly want it to halt if we see a blank right away. So this will cover our buts for that initial 0. Does that make sense to everybody? It's very important that we have this state here to help us kind of dictate this. Now that we have that, we want to be able to keep reading zeros until we hit what? Well, now we can take 0 or more zeros, right? But we want to make sure we don't run into one of these nasty 1s. How do I know when I'm done? How do I know when I'm done? It's when I see the blank, right? Because I already know I have at least 1 0. So I just want to keep reading the input until I hit a blank. Which remember, the blank is a blank symbol is the first thing you run into when you stop reading the input. So we want to make sure we keep going right. If we keep seeing, we want to stay in Q1, our okay-ish state. If we see a 0, notice I'm not really needing to do a whole lot with the actual symbols themselves. That should surprise nobody, given that this is a regular language. But if I see a blank, I want to use this last row to be our final state, meaning we're done. So what I'm going to do is I'm just going to, for fun, I'm just going to be like, okay, well, I'm just going to make it so it writes the blank as a 1. You'll notice that writing to the tape a 1 makes no difference because I care about acceptance or rejection. And naturally, because Q2 is our final state, I leave that bottom row undefined. So as an exercise for you, try to draw this as a transition diagram, but also try to define it with the 7 tuple. So take the 7, try to define the 7 tuple, give its transition diagram. Sorry, I'm getting really excited here. Give its transition diagram along with this, or even try defining this right here formally. So this is the formal description. We gave the transition diagram, but I didn't give you the 7 tuple. So that's something for you to think about. I'll leave it for you. So we're going to take a little pause here. But yeah, so this is some basics about Turing machines. So now you know what a Turing machine is. You know how we define a Turing machine. We've seen how we can do some very basic things with a Turing machine. So are there any questions or anything? And we got some pretty epic spam too. Are there any questions at all before we move on to the next part of this lecture? So the next part of this lecture, by the way, will be on transducers. So you know how I told you about a little earlier, I said, well, sometimes you don't really care about accepting or rejecting. It's more that I want to transform the input into something. That's what we're going to be talking about next. And I'll be showing you some neat things you can do with a Turing machine that aren't just simply just, oh, I changed the A to a B. Maybe it's something else. Like maybe you want to like capitalize letters, or maybe you want to do some other things. Like you want to copy data, or you want to add numbers. So I'm going to show you that. I'm just going to take a little bit of water here. Hopefully that didn't sound any grotesque noise came out of that or anything. But we've seen a couple examples here. But if any has any questions, put them in the chat or let me know how you're doing. I'm going to erase the boards here so that we can get kind of to our next round of things. Because what we're going to do today, just to give you kind of a roadmap, is what we're going to do is we're going to talk about transducers, and then we'll talk after about...
says, doing good, doing good.
Doing good? Okay, good. After we're done talking about transducers, I'm going to give you some concrete examples, because transducers are actually surprisingly important. Some other neat concepts in theoretical computer science, such as what they call reductions, are based on transducers. So, so keep that in mind. The one thing I want to point out to you is, after talking about transducers, dear me, this is really hard to erase. I think I might need to use more water in the future. It's pretty savage. Gotta put my arm into this. I worry if I do this too hard, it's just gonna break the board. After we talk about transducers, we're gonna talk about higher level descriptions of Turing machines, because sometimes you can get the general gist. Actually, sorry, we'll talk about a more tough example.
Says, elbow grease.
Elbow grease, yeah, exactly. What I want to get at is that once we finish talking about transducers, I'm going to show you a more complicated Turing machine that describes a language that currently any of the models I've shown you up to this point can't do. And once we've done that, I'm going to show you. We're going to talk about higher level descriptions of Turing machines, because you're going to see that we're going to come up with some general strategies, such as this one. You know, when I went from left to right and I converted symbols, you're going to see that's like one technique you can use with a Turing machine. We're going to see a couple other kind of programming techniques for Turing machines. So one thing you got to keep in mind is that it's not necessarily that we're like trying to describe these abstract machines. I want you to think of it kind of like we're given the rules of this machine, of how the machine works, and we're trying to program or describe algorithms with the machine. much like somebody might do if they're interested, say, on a computer, say if they're working in like assembly language or something, how you might with a physical computer, you might do something like this with an abstract computer, such as a Turing machine. Here, this is really giving me a fun push here. And I can't put water on it because then that makes things way worse because then it starts smearing it everywhere. It's okay if it's kind of blah, but it's got to be okay looking for you guys. Gotta put my arm into it though. But what I'll do is
Draikou
after
says,
I talk about that.
Lesson plus workout.
Is already outside doing snow. But that's kind of why I was doing it. I was trying to get myself warmed up for this. I guess that was the practice round. Let's see here. Oh man, this is really... There's got to be something in these markers, man, or the board has something going on. Whew. It's worth noting while I'm at it, seeing as I didn't announce it near the beginning, is I do plan on doing game live streams soon. So if anybody really likes watching those, I plan to be starting to do those again. It's been a while. I think it's been like a year.
Kilgriff says, when?
When? Soon, as in, I'm hoping to give you a more concrete date some point this week. So it will be something I'll try to give you guys soon. Oh man, this is really surprisingly hard. Like, I've dealt with some pretty tough whiteboards in my day.
Draikou says, Saga. Draikou says.
The text-to-speech is giving me some interesting... It sounds very interesting. Oh man, this is giving me a good arm workout here. Just about there though. We're just about there. Until it's okay enough. Because you know how I draw the zeros and stuff. If there's any funny symbols on this board, somebody's going to confuse themselves very quickly.
Are you game streaming Romancing Saga? Alayami Sunday says, hello.
Let's... Hello. Welcome on down. We're just getting ready for our next part of the lecture.
Says, how are you doing?
Oh, good. No, good. No, I just wanted to just get in between the lecture parts. So we finished talking about what a Turing machine is. Now I'm going to tell you some neat things you can do with them. If you are interested in converting input into output. Just right now, the whiteboard is being a little uncooperative at the moment, where normally I'm able to very easily erase things, but it's decided, nah, I'm just going to be as rough and tough as it needs to be with the board. Okay, here we go. I think this is okay enough. Usually I prefer having it look nice and clean for everybody, but we'll...
Kilgriff says, gotta use that elbow grease.
But if I put any grease on here, it's gonna get way worse. It's not the elbow grease though. So let's head over here. But no, I hope everybody's having a wonderful day. Okay.
Kilgriff says, gotta use bold and strongly worded language as well.
I guess that works too.
Alayami Sunday says, yes, I'm here because I have something interesting to communicate with you if you have time to chat.
Sure, yeah, no, feel free to put it in the chat. If not, wait till the next kind of intermission. So whenever the chat pops up here, these are kind of like your intermission periods. If you have any questions or anything like that, Usually I'm quite happy to answer questions at any of these kind of intermission points. Usually I try to like remark things if I see them in the chat as I'm talking otherwise. But do note that if ever you don't see the chat on the screen, I can still hear it and I still see it. So even if it's there, I can address it after. Or it's in the next intermission. Let me just see what we got going on here. Just I want to make sure I got some really neat examples.
Also, when are you gonna do a coding stream for your game?
Probably sometime. I don't have a quite set schedule yet for that project quite yet. But most certainly once I get to that project, most certainly it will be the case that I will do some of those types of streams. Let me see here. I just want to make sure because I have a lot of fun things in front of me here that I wanted to show you. Transducers. Just want to make sure I got everything here for us. Okay. Excellent. Excellent. Okay. So what we're going to do now is we're going to move into the next part of our lecture. Give me one moment here. I'm just going to grab one quick thing. Oh, man. It's always fun when I'm dealing with little things. Because, again, like I said, it's been a little while since we've done this together. And so there's going to be a little bit of technical things here or there as we're having our fun here. So let's get back into everything, okay? So we're going to talk about transducers here. Okay. So earlier I'd shown you what a Turing machine is. I gave you some background on what Turing machines are. And we talked about a couple basic examples of Turing machines and how they work. So namely, we talked about this idea of halting. We talked about this idea of accepting or rejecting input. But it's worth noting that sometimes, as we actually seen with one of our examples, this idea of accepting and rejecting doesn't actually make a whole lot of sense to do. You want to think more about Turing machines as this more functional machine, as opposed to a decision-based machine where it says yes or no. I just want it to perform a task. I want to do some sort of function. I want to take the input. I want to do something with it. Many formal concepts in theory of computation come from the idea I'm going to show you here. Namely, you may have heard of things such as, you may have heard of something called a reduction, for example. They're actually built on this idea that I'm going to show you in a moment here. So we're going to talk about what our special kind of Turing machine is called a transducer. So we're going to talk about transducers. So just as a reminder, like most computers output from input. So maybe I would like to have that for my Turing machine. So our machine's output could be left on the tape. On the tape when the machine halts. So once the machine processes, I want it to stop, and whatever's on the tape, I want to be able to interpret that as output. Okay? So that's the main idea here. So very often when we think about a transducer, I imagine I'm given some input. Oftentimes that input may be given as some sort of collection of values. So often we like to think of it as I give you like the first value of the input, some separator or comma, whatever kind of symbol. I need some symbol to separate them, which often are called separators. I'll have the first value, separator, second value, separator, third value, separator, and so on. This is very, very much in the same vein as like I gave you a function, it has inputs, I need to encode that onto the tape so I can use it. So that's the idea I want you to keep in the back of your mind. So as I've said before, Turing machines, well, we have thought of Turing machines as recognizers. So that means give me some input. It tells me yes, accept, or reject. But mainly we're interested primarily in acceptance. So if I give you an input string, it's got to tell me yes, that is a string of the formal language I'm interested in. Or if I'm answering some question to a problem, I want to know when the answer is yes. So Turing, so we'll talk about Alan Turing. Turing actually considered, that consider is very interesting, considered originally a computer of integer valued functions in a manner like we will see. So in Turing scheme, each integer, so we're given these integers, which are encoded. They may be encoded in unary or binary, and so on. And the idea is that I take in input, I leave output on the tape. So we will consider special kinds of Turing machines called transducers. And since we're not interested in a final state or accepting or rejecting, and when defined, the set of accepting or final states is typically omitted because we're not interested in accepting or rejecting. We just want to do some processing. But that processing needs to finish at some point for the transducer. So you know how I gave you a 7 tuple? You're going to think of this as a 6 tuple. So you're just going to chop off the last object, which is the set of final states. So if you start seeing 6 instead of 7, that's why. We don't care about accepting and rejecting. But let's talk about it now. Let's do an example. So I promised you we would see how we could do some things with these Turing machines. We already seen how it can convert symbols into other symbols. In a very basic example, we also seen how to process strings that belong to some regular expression. Let's talk about addition. So we're going to do what we call unary addition. So we're going to consider unary addition. Now, how many of you have never heard of unary before? It's okay if you've never heard of unary before. And you may have heard of decimal. You may have heard of binary. You may have heard of all sorts of different number systems. Unary is actually really simple. So, you know, binary uses symbols 0 and 1. Decimal uses 0, 1, 2, 3, 4, 5, all the way up to 9. So it uses 10 symbols. Unary, the big tip with unary is this part here. It's sort of hiding there, but it means one. It means 1. So this is base 1, okay? So this is a very special numeric base, by the way. It has very strange properties in theory of computation, but it's worth noting that this is what we're going to look at. So, for example, I could give you a number in unary by just using one symbol. For example, I could give you like 0, 0. Those are, so this, for example, there's 2 zeros there. Well, let's put 3 here. This is using one symbol, namely the symbol 0. Some people use ticks, for example. You may actually be quite used to unary before. Don't let the fact there's zeros throw you off. What do you do when you tally? You know, you're sitting there and you're counting things. Like you're watching poor me playing some game and I keep failing over and over again or something. You keep a tally, right? See, like you would have like a tally that keeps count of things, right? So you can have ticks. Well, what you're actually doing is you're counting in unary. Except don't count the whole slashing with a cross. That's a whole other rule. But say, for example, if I have 1, 2, 3, 4, 5, 6, this is 6 in unary. So 6, so that's 6. If I use zeros as the single symbol, this would be 3. But what we'll do for our little exploration here is we're going to use zeros rather than ticks. And instead, I'll use the separator. As a separator, I'll use a 1. Just because it looks kind of like a separator. It kind of separates the zeros. So, for example, if I give you something that looks like this, like 0, 0, 1, 0, 0, 0, what I'm saying is, okay, this number, that's 2. This number, that's 3. Because it's the number of zeros. Is that clear, everybody? So, this is just another way of representing a number. We're only using one symbol to represent it, though. So notice I have 2 zeros, so that's the number 2. I have 3 zeros, so that's the number 3. So when I write out and I want to add numbers, like I said just a moment ago, I want to give you the values as input, and I want to do some processing. So what it's going to look like when we consider adding two numbers in unary is I'm going to give you some number in unary, and then I'm going to have a separator, and then I'm going to have some other number in unary. I have a question for you. Question. What's 0 in unary? What's 0 in unary? It's like the number 0. So most certainly, like, if I give you like this, that's 1, right? It's not 0, right? Because that's just the symbol. It's no different than if I wrote only one tick down. But what's 0 then? It's not the symbol 0, right? What we care about is the number of the symbols, right? So if it's 0, how many zeros are there written down, say in this kind of form like this? What would it look like? So say, for example, I want to go 0 plus 1. So for example, what I'm going to be doing in this example is I would like to add these two numbers and I want to get the result. So for example, I would want to get it so it could be 5, where the answer should look like this, right? So if I give you 0 in unary, it might look something like this. So notice there's no zeros over here, but I have like 1 0 here, so it makes that 1. So this would be like 0 plus 1, which equals 1. So the answer here should just be a single 0. So what I want to show you is how we can come up with a Turing machine that adds numbers in unary. And believe it or not, it's going to feel like we're cheating. Because unary is very simple. But does everybody get the idea of how unary works? So it's no different, other than the cross rule that you use when you're tallying, when you count up 5s or 10s. It's no different than tallying. So how many ticks there are, or how many zeros I write, whatever symbol I decide to use. If I want to use happy cat faces as the symbol, I can use happy cat faces. It doesn't matter. The whole point is that it's the number of the symbols. That tells me the magnitude, or what the value is. So don't let the fact there's zeros throw you off. They're just the number of symbols that matters. So what we're going to do in our example here is we're going to come up with a Turing machine. What we're going to do is we're going to perform addition. Where where numbers are in unary, separated. Let's go separated by a marker. So first, we're going to have these numbers. The numbers are going to have the form as follows. So I'm going to use zeros to represent the quantities. I'm going to use a 1, like I said, as a separator. So I know what the two values are. Assume input. So this is an assumption I'm making. So assume the input is given in the form. So it should look like this on the tape. It should be 0 to the m, 1, 0 to the n, where m and n are greater or equal to 0. So if you're not familiar with this notation, the exponent says repeat what is written there that many times. So for example, if m is 2, this says write 2 zeros. If this is 3, this says write 3 zeros. So keep in mind that if it's the exponent's 0, then it's just the empty string, because I wrote no zeros. So let's think about this. So what should the output look like then on the tape when we're done? What does unary addition actually do? Think about it. Okay. Like I said, it's going to feel like we're cheating, but it's not. This is how it works. And there's many different Turing machines you can describe to do this. So for example, I have two examples here. I have like 2 plus 3 gives me 5. I have 0 plus 1 gives me 1. So what can I say that looks like what actually is happening if I want to get the answer? Well, remember, the number of times I write down the symbol is the magnitude of it's the value, right? So think about it. Okay. Now I'm going to do something, and you're going to see it. Just watch. I want you to carefully look at this example. Remember, this is just an example. So I have 5 over there. It's 5 zeros. Watch this. Look at that. There's 5 zeros. So if there's any way I can get rid of that separator, I can get the answer. So if I could design a Turing machine that takes and removes the separator and then shuffles the zeros over in some way, then I'm done. So that's what I need to come up with as a transducer. So remember, a transducer is just a special kind of Turing machine. We call it a transducer because it doesn't accept or reject. So let's figure out what we're going to do with this. So remember, now that we know that, what should the answer be? So the output that should be left on the tape then should be 0 to the m plus n. Boom. So now we have to come up with the machine now. Let's do that. So let's come up with a machine now. So remember, we want to come up with this one main idea, is we want to get it so we can get rid of that separator. But here's the thing. There's a lot of ways we could do this, and if we do it the wrong way, we're going to get the wrong answer. So we have to be careful. So first, here's an idea. Well, let's kind of bat around a couple ideas of how we could do this, okay? So I have like 0, 0, 0, 0, 0, like this. Now, let's kind of see a couple ways we could go about this and see if they make sense or not. So first, I can have zeros. So this, remember, this is just an example. The Turing machine needs to work with an arbitrary string that looks like that. So let's see here. So what I could do, here's an idea. I'm just going to throw a couple ideas out. One of them ultimately has to make the most sense. So maybe what I should do is see if I can find a 0. Maybe I like go over here and then I move back here and put a 0 here. Maybe I can like do this. That's an idea. That's maybe one idea maybe we can try. Anybody see any problems with that approach? Anything interesting about that approach? So reminder, what I did was I looked for a 0 on the rightmost side. I turned it into a blank, then I moved left, and then I put a 0 where there was a 1. Is there any ideas of what's going on here and if that makes any sense to do? So is there any assumptions I'm making when I do something like that? Well, let's think about it. Let's walk through the process again. What I did was I took a 0. So I went right. Remember, the turn machine will start here. I would make it go right. I go here, put a blank there. Then I would switch to another state that goes and searches left for a 1, and I replace it with a 0, and then I would stop. What's the underlying assumption here if I do something like that? Well, what's actually kind of neat is that this won't work in general because remember we have the situation such as this where it's like 0 plus 1 where I can have no zeros. Well, what if it's 1 plus 0 and I go seeking out a 0 after the separator? Well, let's look at it. Let's see what this would look like. So this would be like if it was 0, 1 like this. Well, I would go look past the separator and I'll go find a 0, but I won't find a 0. Well, that's a problem, right? I can't do that. So this idea would fail. So I can't use that approach. So I have to consider the fact that it could be that there's no zeros on the left-hand side of the 1 or on the right-hand side of the 1. So we have to be a bit more careful about how we think about this. It's not as simple as just I need to do something to move to put a 0 somewhere, but I need to make sure I do it carefully. So it's not necessarily that I need to I have to be a bit careful, right? So let's think about this. So maybe I should think about this a little differently. So we know that approach doesn't work because of this edge case. Because and the underlying assumption is, and keep in mind that's just as true if I were to take it from the left bank of zeros. It's because I've assumed here that it's actually that I can have no zeros. That approach might make more sense if I had at least 1 0. If I always had at least 1 0, then maybe an approach like that might work, depending on what the assumptions are with those zeros. Okay, let's think about it. Let's think about, let's go back to this example again. Remember, these are just to help us think about it. This is not showing us that it works arbitrarily, okay? So let's think about this a little differently. Because remember, we know as a matter of fact, there could be the case that there's no zeros right here. There could also be no zeros right here. However, I always know there's a 1. I always know there's a 1. So on the input, if there's no zeros, it'll just be a 1 first. So I have an idea. Why don't we focus on the 1 here and then try to find the last 0 and then make that a blank. So let's see what that would look like here. So I would search for a 1. I find the 1. I change it to a 0. So I go that way. I change it to a 0. Then I look for the last 0 by going right. And then I turn it into a blank. Interesting, right? So notice that this seems to work for this particular example, right? Well, how about let's look at for example the one we had over here that didn't work. Okay, I'm gonna locate the 1. I change the 1 to a 0. And then I'm going to now look for the last occurring 0. Notice that I'm at the last occurring 0, so I'm going to turn that into a blank. Interesting, right? So now this seems to make sense, right? Do you see how instead of assuming there is a 0 and I'm going to go erase it, I'm going to go and assert that 0 is to exist, and if I can't find it, I get rid of the new 0 I added. So it's kind of like +1, -1, that kind of thing. So this idea, however, seems to make a lot more sense. So why don't we design a Turing machine that does this? So let's take a look. So let's think about how this would go about. So I'm going to describe this using a transition table. And I'm going to give a description of what's happening for each of them. So I'm going to give each state a job. And you'll find with Turing machines, this makes a lot more sense to do than, say, with previously when you think about like DFAs. Here it actually makes a lot more sense to talk about them like as them having jobs or a task that they're doing. So we're going to have a state. We're going to have, remember the different tape symbols. We'll have a 0, 1, or a blank. And then we're going to have a description. We'll have a description. So we're going to have, now remember, let's walk through this process again. What did I do? The first thing I did was what? Remember, if I have like, what I do? I find the marker or separator, right? That's the first job I have. So that's maybe the first state's job. So for Q0, what I'm going to do is I'm going to find the marker, and we're going to make it 0. That's what Q0's job is. That's its sole job. So think of this like we're trying to think of it almost like we're taking the problem and decomposing it into pieces, which a lot of people, especially if they've done any programming, this is a pretty common way of thinking of problem solving. And you're going to find that this is actually rather helpful here. Is you break the task into smaller pieces, you assign those maybe to different states. You may need 2 or 3 states to do it. It's hard to say. Depends on what you're looking at. So let's think about this. So if I see a 0, what did I do? I go past it, right? I want to find the 1. So we're going to stay in Q0. Remember the 3 things we need to know. The state we're going to change to, what tape symbol you're going to write, and what direction you're going. So I want to keep going right until I find the 1, right? When I find the 1, I want to go to my next job, my next task. So I'm going to replace the 1 with the 0, just like what I'm going to do. And I'm going to go write 1. And if you see a blank, definitely don't do anything. Don't do anything. Remember, we're working on the assumption that the first symbol we're going to see is either a 0 or a 1, not a blank. So that's the first state. Next, we need another job here. We're going to try to find the last 0. We need to search for it. Now, this is where it gets a little bit funky. We have to be careful. Because how do we do that? We have to be very careful about this, right? Because remember, we can always have the funny edge case. Like here it's fine. Like I can like, okay, I change that to a 0. And then I go searching. I scan all the way. Now, do I want to stop here? Well, on a Turing machine, you don't know if you hit the end until you see the blank, right? So we're going to need to keep going until we see a blank symbol on the tape. So we're going to have to like find the blank symbol first, then we go left, and then we can delete. And since I've introduced a 0, this will always take away a 0 if I were to think of it like that. So what we're going to do is we're going to go as far right as we can over the zeros until we find a blank. Does that make sense to everybody? I'm hoping that makes sense. Because we need to know when we hit past the input. We need to go past the input to actually do this. We can't just stop here. We don't know if there's another 0 after it. So if Q1, we're not going to change any of these zeros, keep them the same. We know there's no more 1s, so we're just going to keep going. But we want to go into the next state once we see the blank. So we'll leave the blank alone, and when we get that, we hit the blank, it's going to move the tape head 1 to the left. And if we do that, that will land us where we inserted a 0. But we're not quite done yet, right? We have to actually erase the last 0. Let's erase the last 0. So when we actually find it, so for the sake of ease, what we would do is we would turn that into a blank. But let me show you what it looks like for that funny edge case. So say, for example, it's just a 1, where there's no zeros anywhere. The answer here should be 0, right? So it should just be blanks everywhere on the tape. So we know it starts here. This gets changed to a 0. It moves the tape head to the right, finds the blank, and says, okay, well, now go to Q2, but on that you're going to go back left. It'll land you right here, back on the 0. Now we need to turn that into a blank. And we know the 0 always exists because we took a 1 and turned it into a 0. Somewhere. There has to be at least one of them. That's that one of these zeros that's sitting there on the tape, which we just had to have found, most certainly is the one that we need to turn into a blank. So we're going to erase the last 0. And then finally, we're going to move into the final state. But remember, transducers don't have final states, right? We just want it to halt. And there's your Turing machine that takes and adds 2 unary numbers. So if you were to take and draw out some tape, your tape, and do what we did in some of our earlier examples, with this transition table, you'll be able to take any 2 unary numbers. If you write the value in terms of the number of zeros, you'll be able to add 2 numbers. Neat, right? So I'll leave it up to you if you want to draw this as a transition diagram. And remember, it has no final states, so you're not double circling any states if you're drawing one of those. It just has a start state if you're thinking about like special states. Okay, so that's a pretty neat example, right? Let's do something a little bit more involved now. So let's head over here. You know, it's starting to get easier to erase it the more I write on it. It's not very surprising to me that that's the case, but that's not ideal either. Oh, man. Okay. So let's go do another example here of another transducer. So a reminder, that's just a Turing machine that does not accept or reject. It takes the input and it produces output. That output is left on the tape. So what I was thinking as a fun little idea is we're going to try to capitalize letters. So I want you to suppose that we're given a finite string of lowercase alphabetical letters. So for example, somebody gives you the word cat like this, no spaces. But it's worth noting that it won't be very hard to take our Turing machine and modify it so it has this ability. I'll leave that for you to think about. Or other words like spot. And maybe, I don't know, like turtle. So as input, we are given a string of lowercase English letters. Of lowercase English letters. So what I would like to do is I would like to output a string of the same symbols except capitalize. Except capitalized. So for example here, if I want cat, I want it to be capital C, capital A, capital T. For spot, I want it S-P-O-T, all capital letters. And turtle, I want it to be T-U-T-L-E. So a lot of programming languages will have something like this, some sort of thing that's like to upper or something of that sort. So I'm going to show you how you can come up with a transducer that does something like this. So believe it or not, I've shown you actually a really basic example in an earlier case where we swept from left to right, replacing letters with another letter. What we could do is something very much like this, where we scan from left to right across the tape, starting at the first symbol of the input. And whenever you encounter a lowercase letter, you're going to stay in the same state, but you're going to scan one symbol to the left after you have replaced the lowercase letter with its uppercase counterpart. And that's actually all you need to do. So for example, if you imagine you have your tape like this. Remember, there's blanks on all around here after. So if I have like cat, for example, if the tape's here, I would like it to just replace, like right on the tape, capital C instead. Move the tape one left, sorry, not left, right. Uppercase A, move it to the right, uppercase T. And when do we stop doing this? When you see the blank. But now, I need to be a bit careful here because remember, what we usually use is as a blank symbol is capital B. So what I'm going to do now is I'm going to use a different symbol just to illustrate that you can use a different symbol. So I'm going to define our Turing machine. So here we go. So let the transducer TM TL be equal to the following. It's going to have two states. We're going to call them QR and QF. Its input symbols are going to be lowercase English letters. Its tape symbols, remember, now this is one thing you have to keep in mind, is that the tape symbols include the input symbols. So you have to put all of those in there too. A, B, C, all the way up to Z. Uppercase A, uppercase B, dot, 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 all the way uppercase Z. And then we're going to need a blank symbol. Now, in my notes, it's easy enough to see the difference between the type-faced B or an alphabetical B versus a fancy B. So I'm going to instead use a big box that looks like this, just to make it a little bit clearer that it's a blank. Next, I have to give you the transition function. The final state, the start state is QR. Remember, that's a start state. Remember, we don't have final states, right? And the blank symbol is this box. It's technically a rectangle, but I'll leave that here, there, and there about the debate of whether boxes are rectangles and squares and rectangles are the same thing. That is not what we're going to discuss here. So, let's now define how this will work. So we have an idea already here, which this is nice, where delta is defined by the below transition table. So I'm going to use a transition table. Now this table is going to be a little bit kind of clunky to look at, just because it has a lot of columns. So I'm going to omit a whole bunch of the columns just for the sake of brevity. So it's going to have two states, QR and QF. It's going to have A, B, dot, dot, dot. Z, lowercase z, to be a bit more precise. Uppercase A, dot, dot, dot. Uppercase Z, blank symbol. So those are the columns of our transition table. You might ask, Dan, why have so many columns? Since remember, each of the columns, there has to be a column for each one of the tape symbols. So keep that in mind. It's really important to remember that. So you might ask why I put all these dots in here. It's because I'm going to represent the table by truncating the rows and columns appropriately. So if I could describe it carefully enough, I don't have to write every one of the rows, every one of the columns. There's a lot of columns here. So remember, the whole idea is that if I see a lowercase a, I want to put it as an uppercase a, right? So I want to continue to read. So I'm going to call this QR because I want to think of this as read, and F to be when I'm done, when I'm finished. So I want to imagine I'm reading the words. So I replace the lowercase a with a capital A, and then I move right one, like I did here in our example. I'll do the same thing with the lowercase b. So I stay in QR. I replace with a capital B, then I move right. I'll do this for the C, D, E, with their corresponding uppercase letters. Lowercase z, we're going to replace that with an uppercase Z. It's kind of hard to tell that they're lower or upper, but my hope is that you'll get the impression by how tall it is. It's the big boy of Zs, okay? But notice that A, we don't read any uppercase letters, so these are all really easy for me to describe. It's just undefined. But when I see the blank, that's when I know I'm done reading. So I switch over to QF. I leave the blank as a blank. Now, I don't want to use a B here because the symbol is now this symbol here. So I'll go right. And now QF's really easy because this is a final, well, it's not technically a final state, but I'm using it to halt the machine. So all of these in the second row don't have any moves defined. Whoops, I need dot, dot, dot. Because I want it to halt. Now, believe it or not, there's actually an alternative way of formally defining this using actually the formal description of the transition function, which arguably looks a little nicer than this if you define a function that takes each lowercase letter and outputs the uppercase letter. I'll leave that in my notes if you're curious about this afterward. So this is how you can come up with a Turing machine for which it will take lowercase letters and it converts them to uppercase letters. This one adapts a very simple strategy of just going from left to right. Now, I'm going to show you another example. Let's go over here. I want to convince you that with a Turing machine, you don't necessarily just have this system of of replacing very basic symbols with others, and you don't necessarily just have adding, you could copy data. Because you got to think of the Turing machine very much like a symbol manipulation machine. The minute you start thinking of it more like that, its possibilities start becoming a little bit more apparent. Because what's on the tape can be modified, and you can use more tape cells if you need more. So I'm going to show you how we could come up maybe with a Turing machine that copies data, but we're going to keep it really simple for this example, but the idea should be fairly easy to generalize. If, say, you wanted to consider binary, for example, I'm just going to use unary. And just as a reminder, unary just is where you have only one symbol. So in this case, I'll just use a sequence of zeros, but in many systems, you'll think of it as just a bunch of ticks, where the number of ticks indicate the value of the number. So what we're going to do, let me just erase what I have over there. Okay. So next for this example, we're going to consider how to copy. So now if we're thinking about like a unary number, like it's 0, 0, what it means to copy is to take what is here and concatenate it with itself. So this would be, for example, a copy of what is here. So what I want to do is take the input, I want to concatenate it with itself, creating a copy, doubling the length of the string. So that's what we're going to be trying to do here. So let us design a Turing machine that takes the input, and concatenates a copy of the input. So just to give you an idea of what we're assuming, the numbers are in unary. They're in unary, separated by a marker. The form assumed is 0 to the m, where m is greater or equal to 0. That means it's going to be the number 0 in unary. It could be the number 1, number 2, number 3, number 4, number 5. It could be any non-negative integer represented in unary. So if you think about it, the way I would describe this, it should be 0 to the m concatenated with 0 to the m. That's what I should look for. Now, I'm going to show you a technique. This technique is rather valuable when you think about Turing machines, okay? Because you start having to remember things. And remembering things can be a little tricky if you're not aware of a very simple way of pairing things. Because sometimes when you're counting, it's unclear, okay, do I have the same number of objects or do I have a bigger set of objects on one side versus another side? Now, what we could do is we could use a very simple technique of pairing elements to count them. And that's actually what we're going to do with our Turing machine. So, for example, you know that this is correct because I can pair this one with that one. I can pair this one with this one, right? That's how I know that I did it correctly, right? But you'll notice it gets kind of hard for me to tell the difference between this group of symbols and those group of symbols as I'm doing this, right? So you're going to see that I'm going to have to be a bit careful about this. So here's an idea. Seeing as it's an example about copying, maybe an interesting idea. So here's an idea. Here's an idea. So we're going to convert all the zeros to a symbol C. So we're going to call it C. Then go left to see the first encountered C and change it to a 0 and immediately that's supposed to say immediately, by the way. It's supposed to say immediately. It sort of melted over there. It was having a dream and it kind of woke up a little too fast. And then immediately adds a 0 on the rightmost end. So let me walk you through what I'm saying. Okay. So over here I was like, okay, well you kind of pair them, right? Well, think about it this way. So you start off with 2 zeros. That's the input. Okay, so what I'm suggesting is instead of having zeros, turn them into C's. And then what you're going to do is, now it doesn't technically matter which of the C's we go for first. We're just going to go with the first encountered one. What we do is we change the C into a 0. And because I encountered a C, that means I need to pair it with a 0. So what I do is I go right, I put a 0, because that pairs it up with one C. Then I go back and try to find another C. I replace that C with a 0. But because I found a C, that means I need to pair it. So I end up with a 0. Hence I get 4 zeros. That's the idea. And this technique, by the way, is colloquially called zigzagging. Okay? Some people call it zigzagging. So some people call it zigzagging, or they're performing a zigzag. So the idea is that you pair elements to try to see if you can find another one. And the minute you can't pair them properly, something needs to happen. So here we go. So now if we have, has everybody got the idea? The idea is I'm just going to try pairing elements after I've presumed I haven't counted or paired them yet. So every time I find another 0, I'm going to add another 0 onto the end on the right. And until I no longer have any C's left. So what we're going to do is we're going to consider a Turing machine. We'll call it T-copy. T-copy will have 4 states. Now, I want you to think carefully about this. First, what we did, the idea we have up here, is we start off with just by replacing the zeros with C's in the input. That dictates needing a state. Next, we start doing the zigzagging, right? We start going back this way to find a C. So we need something to do that. And maybe we need another state for copying the 0 on the end, like when I took and paired it off. then I need something to tell me when I'm done. That seems pretty reasonable, right? That seems pretty reasonable. So let's go with that. So we're gonna call it Q0, that's the start state. We'll also kind of colloquially call it Q0 because it replaces the zeros. We'll have QS for search, QE for add to the end, and QF for when we're done. The input symbols, we just have zeros, nothing interesting. Tape symbols, we're gonna have 0, C, and the blank symbol. We're gonna have the transition function. We're gonna have Q0 as the start state, and then we have the blank symbol. So remember, a transducer has 1, 2, 3, 4, 5, 6 of these guys, not 7. It's a 6 tuple, not a 7 tuple, because we don't have final states. Where delta is defined by the below transition table. So we're going to need a table. I'm going to do one just because these get a little bit more complicated. What I'm going to do is I'm going to, again, so I have states. I'm going to probably have 4 of them. This is just me kind of brainstorming as we're kind of doing it together here. I have 0, C, B, and then I'm going to have a description. So let's kind of walk through what we had in our heads. So we're going to replace all zeros with C, well, C's. So that's kind of what we want Q0 to do, right? So that's what we need Q0 to do. So let's see. So if we see a 0, we better turn it into a C. So we're going to stay in the state. We'll go right. If we see a 0, we replace, so we stay in the same state, we replace zeros with C's, and we go right. C, we don't have any C's at this stage that we're going to encounter. Once we see a blank, that means we've hit all the way to the right, meaning that we can now start this pairing process by zigzagging. So we have QS, blank, left. So if I go all the way to the right on my tape, like when I had the 0, 0 that I replaced with the C's, there'll be a blank right here. I want to make sure I put the tape back to be right here. Let's start the head, the tape head. Sorry, I'm getting really excited. So I have Q0. So now we're going to search for a C. That's the job of this next state. Now, question. When do we finish this searching process? We do it when we hit a C, but what if there is no more C's? That's when we want to end the process of this, and means that we're done, because we're done pairing them, right? That's what we said when we were kind of playing around with our little example over there. So let's play around with this now. You most certainly want to make sure that we want to hit a C, but we might run over some zeros while we're there. So let's make sure we stay in this searching state. We leave the zeros as they are, and we continue going left if we see a 0. If we see a C, that means we now need to pair it off. So we're going to go into that go to the end, add a 0 state. So I'm going to replace the C with a 0 because now I've counted it. We're going to go right. And I'll start us on that process. If it is a blank, however, we know we're done, right? We didn't find a C. We failed to find a C, so that means we need to wrap this up. So we go QF, blank, and left. So now that we have our task for which we're searching for C, now if we're successful at finding C, we will be in QE. So that means we're going to stay in QE. If we see a 0, we'll go right. We're going to pass over any zeros. However, we're not going to run into any C's because we're going to do this until we hit the first C. However, when we see a blank, we better replace that with a 0. So we're going to go back to the search phase and try to find us another C, because now I'm going to append that 0 on the end where a blank is. And I go left. So this will copy 0 to the end. And naturally, what's the last row going to look like? It's not very interesting. The row's not very interesting. QF is just going to have, we're not going to define these, and we're just going to halt. Boom. So there we go. There we go. So now we can see how we can use the zigzag technique to copy data on the input tape. And like I said, you can actually take the idea that we have, even though it's the unary here, it's not very hard to take and adapt this idea to copy more generalized data. It's all based on the zigzagging idea and having enough symbols such that you could represent each one, so that when you could keep track of the data that you're copying over. Pretty neat, right? That was pretty neat. So are there any questions? Any questions at all? So I want to show you a few examples of these transducers before we get to kind of the next part of this. So is there any questions? How's everybody doing, by the way? Hopefully I've not murdered anybody. I'm just going to erase the boards.
Draikou says, doing good.
Doing good? I know. That makes me happy. That makes me very happy. So we're going to erase this. But if there's any questions, I'm happy to answer any questions at this point. Keep in mind that I'm happy to answer questions about the examples that we've seen here, the transducers.
Tracy Me210 says, my cats are begging me for attention.
They love doing that, don't they? Just got to give them the attention. It's important to give them the love and attention, those kitty cats. Oh, man, no. So just as a reminder where we are, so I told you about Turing machines, what they are. We've seen some examples of how they work. We talked about how we can use them as functional machines that take input and they produce output. I showed you a couple techniques so far. The next example I'm going to give you is actually going to use the zigzag technique that I just showed you. So what we're going to see next, so let me give you kind of a roadmap. So what we're going to do is we're going to see a language. So for those that aren't aware, formal language is a set of strings. A lot of these different models of computation, the way they work is that we're often curious about what problems you can solve with those models. Or, in other words, can you determine if an input string belongs to a language or not? So that's the notion of acceptance and rejection. So I want to ask if a string belongs there or not.
Finally getting them gains.
Like I said, the more I use it, the easier this is getting. So it's not perfect, though, I will say. The one thing I want to point out is I want to show you that a Turing machine, as we've defined it, is capable of describing more formal languages than any of the machines I've shown you up to this point. And I'll show you an example of one such machine that can describe a language that's not context-free. Once I'm done doing that, we're going to see how I can, now that we'll have kind of like these tools, like ways to design Turing machines, how I could describe maybe at a higher level how to solve a higher level problem. And then I'll define how we know what a language is for a Turing machine. That'll be basically where we're going to stop. And where I'll kind of conclude where would be a very natural place for us to talk about more kind of like ways we could beef up the Turing machine or capabilities of the Turing machine. Or even some fun things about counting. They're all really interesting. Let's just gonna drink a little bit of water. So if I make any weird noises, that's why. There we go. There we go. But no, this is really exciting. I'm really happy to be doing this with you. I missed hanging out with everybody on here. I'm hoping to do this a bit more often. That and also the other live streams too, because I think we have a lot of fun doing that kind of stuff. Let me see. I just want to make sure we're in the right spot. Here, So one thing I will note, for anybody that's on that wants access to these notes, they'll be available later today on the Patreon at patreon.com/pagewizard. Supporter access and above, I believe that's just, I think it's like $5 or $6 a month Canadian, which is like in Monopoly money compared to American bucks. That's nothing. That's like nothing. People pay hundreds of dollars for these things. Sometimes more, sometimes less, but definitely not that. So I'm hoping you'll be considerate if you find this lecture really interesting, that if you want to get some of the notes and some of these examples, that's one way to get them. There's alternative ways also to support in a very similar way, such as with PayPal and also with Subscribestar. And all of them, well, specifically Patreon has different tiers. For example, if you want access to the Discord server, there's also that's available at the, I believe it's the, you would have to go to patreon.com/pagewizard. I'm thinking about Turing Machines a lot today. I think it is basic support and up, which is the $10 tier. If not, it's like I said, I'm not too worried about those types of things. But if you're curious about a Discord server where supporters could go do things, or you want to get updates back behind the scenes, the notes, there are even tiers for access to the book, one of my data structures books. A lot of these are available that you can check out and can help support keeping the lights on here. So let's I think we're ready to get on to the next part, and I'm really excited about this because we're going to start talking about some things that these machines are capable of doing that none of the other models I showed you in our earlier videos about theory of computation are capable of doing. And remember, this machine, all it is just kind of goes left and right, and it just reads stuff and writes stuff. That's all it does. It's nothing special other than we just added this read-write ability, okay? So, read-write, and the head can go back and forth. If it just goes this way, zip in one direction and read only, that's just like a DFA, like a deterministic finite automaton. Just gonna get a little bit more of a chunk of water, but if anybody has any questions, you let me know, okay? Hope everybody's having a wonderful day. I'm not kidding. I've been psyched up to do this like for days. So what we're gonna do. So I'm trying to think if we want to go over there or not. Maybe we'll start over on this side. So let's get started. Is everybody ready to go? I'm ready to go. Show me some love in the chat.
Draikou says, ready.
Okay. Just want to make sure, in case anybody else wants to get some love. I feel like I'm just like pulling teeth. It makes it a lot more fun.
Well, Tracy Me 210 says, set go.
Yes, let's go. Okay, so let's do this. So previously we had seen some examples of transducers, and now I want to return back to our definition of a Turing machine. Now, I want to do next is I want to show you a Turing machine that's capable of recognizing a language for which it isn't context-free. That means that there does not exist a context-free grammar for which it can be described, nor does there exist a push-down automaton that you can use to recognize it or even decide it. So what we're going to do is we're going to try designing. So we're going to designing a Turing machine for a non-context-free language. So the one we're going to be interested in is going to be the following one. We're going to call it L1. L1 is going to be a to the n, b to the n, c to the n, such that n is greater or equal to 1. Now, you might ask, what the heck is that? This thing here, what it is it's the set of strings of A's, B's, or C's, where the number of A's is equal to the number of B's, and the number of B's is equal to the number of C's. They all have to have equal numbers. So for example, like A, B, B, C, C, that would be a string that would be in this language, this set of strings. So I would want to design a machine such that it'll accept on strings like this, but it will not accept on strings that look like this. Is that clear, everybody? So it's worth noting that you can prove that L1 here is not a context-free language. I will not prove that here, but I'm just telling you that is in fact the case. But what I'm going to do is I'm going to show you how I can use Turing machines, almost like they're subroutines for a bigger Turing machine. Kind of like having a little function or method for a program can be used to solve a problem for a bigger computer program. So what I'm going to focus on for now is I'm going to focus on a different language that's kind of like this one. And I'm going to see if we can use our technique of zigzagging to help us. So first, let us adapt some of our ideas to design a Turing machine for this language. For L2 is going to be equal to a to the n, b to the n, such that n is greater or equal to 1. So we're going to use this Turing machine we're going to cook up to help us get a Turing machine for L1. Now, for anybody that's not familiar with this one, this language is not regular, but it's context-free, which is why I think it's kind of neat. So this one is saying that the string, so the input has to have equal numbers of A's and B's, but the A's have to be together and the B's have to be together. That's all it says. So you might ask, okay, well, looking for equal numbers of things. Now, if you thought about some of our previous examples, such as when we were trying to copy data, for example, we actually had an idea where we were trying to pair by counting, and we had this thing where we kind of zigzag back and forth, trying to pair them. Maybe we could do something like that right here. If I want to know if there's equal numbers of A's and B's, and they're grouped like this, I should be able to do something like that with that technique. So here's an idea. Match each A with a B. So this is where it's going to get a little tricky, though, because we need to make sure we're not getting weird cases like this. Like, we don't want to be like A, B, like this. Well, they have equal numbers of A's and B's. That is not the form of the string, right? It's supposed to be A, B, B if it's supposed to have two A's and two B's. So we don't want these. So we're going to have to be careful because, like I said earlier, if we want to encode more information, we could use more symbols. So here we go. So what I was thinking is instead of having just like C's, or we'll call them X's and Y's. So by marking each with an X and a Y respectively. So this will help us make sure that we're not having that funny case here. Because if I start having where like, I want to make sure I'm not grouping things in the wrong way. So we're going to adapt. We're going to try zigzag. We're going to try this zigzag approach. So if we can't find a matching A with a B in the appropriate way, we should reject. Otherwise, we should accept if we get it so we can pair them all. So I have some ideas. These are just ideas. We don't have a machine yet. So I want to think about this matching thing. So first we're going to have a start state. So what I want to do is I want to think of something maybe to set it up kind of like a loop where I can like repeat this process over and over again. What Q0's job is going to be kind of like that. I want to be able to keep pairing them up. I need some way of repeating this process until a failure occurs. So ready for reading the next match. So think of it like so it's like a loop. We're going to have QA. QA is going to be going right. We're going to be going right. Going right. Now, I want to be able to like find an A, so this thing's going to probably set me up with an A. So going right after reading an A. So we're going to, so this will be after I mark it, after marking with an X. Because the idea is I want to like mark all the A's with X's and the B's with Y's, and I want to be able to like pair them up appropriately so I'm not double counting anything. So QB, it's for going, we're going to be going left after reading B. So you're gonna mark Y. You're gonna mark Y. Actually, what we want to do is we probably want to do it where it's after. We're going to mark it with Y. So just keep that in mind as we're going to kind of have it where it's going to be finding an A, we mark it with an X. Then we go right, we find a B, we mark it with Y, and then we start going left. Then we're going to have QR. So this is going to be for finishing up. So this is just like a check. So and then obviously we'll have QF. This will be so this will just be a final state. So once the check is successful, then we go to this final state. So this is just sort of a sketch of an idea. We haven't quite formalized anything. So let me give you an idea what I mean by this. So like suppose I have like A. Actually, let's do 2 A's and 2 B's. So what I'm suggesting is we identify first A. Now remember, if this is indeed a string that belongs to this language, there has to be at least one A. That's an important observation to make. So we're going to leave on an A if this is in the language. So if that's the case, we would replace the A with an X. So we're going to go right, try to find a B. Okay, we put a Y there. Then we're going to go back left. We would want to probably like reset this somehow, right? Because we need to make sure we go over everything. But either way, the point is that we're going to eventually have it where we want to repeat this process, where we want this to be an X. And then we have it where we go right, make that a Y, then we go back left. And then we ultimately want to check to make sure there's no more A's and B's, right? If we don't find anything that formats the same way we were expecting, we reject at any stage in this process. Hopefully you understand the main idea. Remember, right now we're just focused on this language, L2. I'm going to show you that making this one for L1, this Turing machine, is actually going to be very easy after we have this. But I think this is a good kind of warm-up for how we can use the zigzag technique. So here we go. So let's try to describe such a machine. I'm going to use a transition diagram because it feels a little bit more natural in this case, because it's going to be a little bit more involved. So we're going to let T2, have the following states. It's going to have Q0, QA, QB, QR, and Q capital. Well, let's see. Do we want B or F? We'll call it QB, just because I think it's fun. Because we want to hit a blank. So maybe I'll call it Q capital B. Then we have A and B are our input symbols. We're going to need those X's and Y's, so we're going to make sure we have those in our tape symbols. We're going to have delta. We're going to have Q0. We're going to have the blank symbol, and we're going to have Q capital B be the final state, where if you're a puppy, it's all good. where we have delta as below. So we're going to define a transition diagram here. So here we go. So this is all going to come together nicely, hopefully. So we have Q0. Actually, I'm going to draw a little bit because I want to kind of adapt this. So let's be careful. So Q0 is going to be the start state. Then we're going to have QA, QB, and we're going to have QR down here. And we're going to have Q capital B. Q capital B. Now, I want to think of it like it's a loop. It's going to repeat this over and over again. But once I'm in that final check phase, it's going to go down here. So let's put the check phase in. So let's take a look and see what we got here. So do note, if we're a little careful about this, like if I had AABB, when I get X, then it goes Y, then it goes X, then it goes Y, then I go back this way. If I have some way of setting it up so that that I see a Y right away, then I can pass through to see if there's any other symbols. So let's take a look at what we could do here. So first I suggested that we ready this up. So if we see an A, we should replace it with an X and then go right. We know that's going to be positioned on an A if this indeed accepts, right? If it doesn't, then it better be rejected because that's not quite right. Okay. Next, we should skip over some A's. If we found an A, we need to skip over A's, right? So we need to go find ourselves a B. We're going to ignore any Y's we run into because I want to find a B. So if I see a B, I'm going to replace it with a Y, and then I'm going to go left. And then naturally, I'm going to want to get me back, set me up for another loop. So I have Y, and I go left. So I want to skip over any Y's. I want to skip over any A's, and I'm going to go all the way back until I can see an opportunity to restart this process. So namely, when I see an X, I want to go right. Because remember, the first A gets replaced with an X. So this will set me up for the next A to be read. Does everybody see that? So the idea is I'm going to take an A, turn it into an X. I'm going to go right as far as I can until I see a B. I replace that with a Y. Then I move all the way back that way until I see an X. Because I remember I replaced A with X initially. So it's going to start filling in x's going from left to right. So when it happens, then I can start this process again. So if there is another x, then it most certainly must be that I'm done. But notice very carefully that it actually puts it 1 to the right. So if it's actually 1 to the right, it'll be where B is positioned. And if there was a correct pairing of them, then there should be a Y present there. Because you notice it'll go like this. See, if it hits an X, it'll go like this, 1 to the right. So there better be a Y there. So I got Y, Y, and I go right. I'm going to go this way because I know I have no more A's to look at. And now I'm just going to continue reading in Y's, not doing anything. I just want to make sure I get all the way to a blank. I know when I hit the blanks, there's no other hiding B's afterwards. And then I have, if I see a blank, I go to the final state. And now this is a final state. I want it to accept. So if you look carefully at this, all I'm doing is, let's walk through this example once again. So A gets replaced with X. I go right, right, until I hit here. Okay, it says replace this with a Y. And it says, okay, go left until you hit an X. Because remember, X was the last, that was the last A we paired, right? So it says, okay, that'll go right, 1, right here. And it says, okay, A. Okay, A, turn that into an X. And now skip over any A's or Y's. And I see B, replace it with Y. And it says, okay, well, now I'm going to go left until I see an X. That puts me right here. But it says go right once I see an X. So it puts me at a Y here. And that will get me to here appropriately. And it'll allow me to skip over any Y's. This will make sure that there's no B's just sort of hiding away somewhere. And I hit the blank, I'm home free, and I'm all good. So this is a Turing machine. So this is a description of a Turing machine for L2. So this will check if there's equal numbers of A's and B's, and the A's come before the B's. So now I want to show you what we could do to get the additional functionality. It's actually rather straightforward. So remember, what we had now was, so now we have A, B, B, C, C. You'll see that we have to pair an A with a B and pair that with a C. So it's A, B, C. So notice all I need is a new symbol. So instead of it just being X, Y, I'll add in Z. So we would have C, so we'll call this T1, C, C, Z, and we'll probably need another state for the QC. And notice that it's not going to change a whole lot. We're going to have, because remember, I want to be able to go boom, 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 and then I want to go back and restart this. Do you see if I have the matching A's and B's? This is no different than going A, B, C. It's just now I have to add one more state to get me go back over here. It's just the same idea again. I'm just going to extend it. So now all I'm going to do is just do this. Instead of it going back now, I'm going to now extend this one state to QC. And now what we're going to do is we're just going to have it so it goes back up a little bit more. So instead of us going back there at this stage, we're going to extend this. So now we're going to go like this. We want it the same exact way we had it before, because that's how we reset the pairing process, right? That's how we reset it all. So now we still have to make some changes though, right? Because we don't want it to go back all the way to the left already here, and it's going to get stuck somewhere that we don't want it to have. So let's change this up. We want to skip. We're going to use the same idea we did here. So instead of it being B's, we're going to do the same exact thing. We're going to make it skip over the Z's, and then we're going to skip over the B's. And when I see a C, I better replace it with a Z and then go, should we go left or right? Let's go left because that's what we did before, right? With what we had before. So what we're going to do is we're going to take Z. We want to make sure if we want to go all the way back to the X, right? So B, we want to not do anything with the B's, the Y's, and the A's. Just go back. That's all we're doing. So far we have it where, so this hasn't really changed a whole lot. It's just this part over here that changes a bit. Now, we still need, so we're going to have to skip to verify. We have to skip over Y still, because we have equal numbers. There's going to be at least one of these. But we need to skip over Z's too, right? Because remember, we're replacing the C's with Z's. And I think other than that, I think we got everything. Let's see, A, X, Y, because remember, we have to skip over, we would have it where we would make this an X, then we would make, well, we'd make that a Y, right? Then we'd make this a Z, and then we would work our way back over here to the X, one position over, X, Y, Z, goes back this way, hits the X, goes one to the right, sweeps to the right. You'll see it's the same process again, except I just extended the zigzag to be an even further zig for my zag. But like I said, this Turing machine is for L1. So L1, it's worth noting, is not a context-free language. So this tells you that Turing machines are capable of recognizing languages that are beyond the context-free languages. In fact, you could do even more. We'll talk about those in a future lecture, but I thought this example would be kind of neat to go off of. So I think I'm looking at our time here, just because I came with a lot of fun material here today. I think it'd probably be a good place. This is actually a good place for us to stop for today. I was thinking, because we've been going for a good while here, and I'm sure I could keep going. I've been going for like 3.5 hours or something like that, a little under that. But does anybody have any questions before we wrap things up for today? I thought it would be, at least this is a pretty nice place for us to stop. When we come back next time, we can always talk more about these higher level descriptions for Turing machines, how you actually describe the language of a Turing machine, and see where we go from there. If not, we might even cover a different topic. So for example, I have a whole bunch of fun material I prepared on tree data structures, namely some properties that they have. So they're kind of neat. But are there any questions? Any questions at all before we wrap it up for today? I'll give a few moments just in case there's any questions. But I thought this would be kind of neat to show you how you can take an idea that already exists and just extend it ever so slightly.
Kilgreave says, JJJJJJ.
I take it we don't have any more questions, but that's a good comment. I love it. So I know I was going to talk a little bit more about stuff, but I'm sure people would love to take their, whether it be, I believe it's President's Day, I think, in the States. If not, it's, we got Louis Riel Day here in Manitoba. I'm sure people would like to get back to the rest of their day after learning all this fun stuff about Turing machines. But what I'm going to do is I'm going to let you guys go. It was so lovely having everybody here, and I'm so happy to be back doing this. So I want to say thank you so much, everybody. And, of course, have yourself a beautiful day. I'll see you later.